Well, I had a bit of trouble when I saw the topic of this meeting, not really knowing what people meant by the multiverse. I think many of the alternatives that I've come across, I would use up all my time trying to distinguish between them. I think I'll comment mainly on what Michio was talking about, namely quantum mechanics, and the issue that in quantum mechanics you seem to have to consider all sorts of alternative things which happen simultaneously. Now the trouble here is the theory, in my view, it may well be, as mentioned earlier, the most successful theory we've ever had. The trouble is it may be successful, but it's not really consistent with itself. The trouble is it consists of two parts. One of them is what one can call the Schrödinger equation, how the quantum state evolves in time, and the other has to do with what happens when we make a measurement. And the two things are inconsistent, because if you imagine making a measurement, then that involves a measuring device, and that seems to come in from outside. The measuring device is not considered to be a quantum system itself. If it is, then it doesn't measure anything. So I have a real trouble with quantum mechanics for this sort of reason. It is clearly a successful theory. It clearly has enormous implications that we see agree with the physical world. However, it has this big blemish. It was quite pointed out by Schrödinger himself. He described this thing in his hypothetical cat, which was dead and alive at the same time, and he was more or less not saying, as some people say, well, maybe if you're clever enough you could build a Schrödinger's cat which was dead alive at the same time. Schrödinger was pointing out the absurdity of the situation, more or less to say there is something wrong with the theory. And that's my view, is that there is something wrong with the theory, even though it is such a wonderful theory. What's wrong with the theory has to do with superpositions which are not just, say, electrons and here at the same time, but big bodies which are here and here at the same time. And in my opinion, if one considers the foundational principles of the other great theory of 20th century physics, namely Einstein's general theory of relativity, you realize that there are issues of conflict between the general principles of general relativity and those of quantum mechanics. And in my view, that it's not just that general relativity has to be quantized, in other words, brought under the general scheme of quantum mechanics, but quantum mechanics needs help itself. And the help it needs is to get rid of all these different alternatives. One thing happens, not the superposition of all the different things. And one can understand that by exploring how general relativity relates to macroscopic superpositions. Now, I'm not going to go into that here, it's not the place to talk about it. But the conclusion one seems to come to is that when you have a big enough body, which is in the superposition of two places, it has a lifetime in that state, which very rapidly becomes one or the other. And a theory which improves upon quantum mechanics brings in general relativity in the right way. It's not quantizing general relativity, which people often say is the major problem of physics, if you like. It's gravitizing quantum mechanics. We have to see what happens when the principles of general relativity are brought to bear on quantum mechanics, and then you see that you don't have all these superpositions of different things at once. You can have one thing or another. The bigger the thing is, the more rapidly it becomes one or the other in a perfectly coherent scheme. Now, I'm afraid that at the moment we do not have a complete theory of this nature. I regard it as the biggest challenge of current physics, to see how to bring these theories together and to rid quantum mechanics of this big blemish, namely the measurement problem, or the fact that superpositions seem to be present in quantum mechanics, and really we want a theory which has one alternative or the other persisting for macroscopic bodies.
Roger, sometimes I think your view is described as a multiverse, but it's a cyclical multiverse. It's the idea that this universe did have something before the Big Bang, and there was a previous universe, and that in fact if you look back indefinitely, there are a whole series of expansions and contractions going on in sequence. Is that right? And would you describe that as a multiverse, or do you think actually you really see that as one universe? It's just that it goes through a series of stages.
It's certainly only one universe. There's no multi-universe about it. And it doesn't contract, I should say, but never mind about that issue.
Yep.
No, the point of view, that's completely different, of course, what I was talking about now is the issue of the quantum mechanical, apparently, multitudes of different things.
Yep.
But yes, what you're pointing out is this model which I put forward some years ago, where you have a sequence of phases, or eons as I call them, but they're all part of one universe. Moreover, things which happen in the one before ours influence ours in ways which are observationally testable. And some of these have been tested, and we see positive conclusions from these things. So I don't regard this really as being, as you were saying, suggesting, I think, that this is not a multiverse in any normal I don't know, is there a normal sense of the word multiverse? But it isn't one in the sense that I've heard expressed. Well, I'm not a particle physicist, so I don't claim to have a better theory than string theory, although I'm pretty disappointed by the conclusions. I mean, just to mention how other theories have taken a long time to confirm, and so it tells me nothing about string theory. I mean, string theory proposes the wrong number of dimensions of space, for instance. It proposes the wrong sign for the cosmological constant, for instance. All sorts of things which have come out of string theory are just wrong. Now, you could get round this one way or another. I know people like to tuck all these extra dimensions into a little tiny ball. They haven't answered the question that I've often raised in my books about that, which is that it doesn't really solve the problem. I mean, there are big, huge problems facing string theory. I don't quite know why we're talking about this with the multiverse anyway, because string theory is a particular theory which I don't think has much in the way of support for it. It's got a lot of people who argue for it, but that's not scientific support. There aren't experiments which support string theory. But that's really a different question from the multiverse, isn't it? Are we talking about string theory or the multiverse here? I'm not sure.
Well, both. String theory has been criticized for being a multiverse theory.
Oh.
But I don't mind, because even if you take a look at Newton's laws of motion, they are also, in some sense, a theory with an infinite number of possible solutions. If string theory has an infinite number of solutions, well, so does Newton's laws, Maxwell's equations. They all have an infinite number of solutions, but how do you make sense of it? By looking at the initial conditions. That's how you can prove that Newton's theory is correct, by starting with a baseball, starting with a rocket. Same thing with string theory. You start with the initial conditions of the universe, and then you can project into the future. The problem is experimental. We do not know the initial conditions of the universe. Therefore, we cannot directly compare it to a multiverse theory. But that's an experimental question, which I think will be answered as we have more and more satellites detect things like gravity waves in outer space.
Michio, some people would say that what we need to do when we're proposing theories is to apply good ancient philosophical principle of Occam's razor, that you generate as few new entities as possible. But the proposal that there's an infinite number of other universes seems on the surface to rather break that principle. Do you not think that a more modest proposal might be more comfortable?
People have tried. People have tried for decades to tear apart the multiverse theory. But as I mentioned, it's a legitimate interpretation of the quantum mechanics. It agrees with all the experiments. Now, there are other interpretations of quantum mechanics. You don't have to believe in the multiverse theory to get 10 billion, 1 part in 10 billion accuracy for an experiment. There are other interpretations of quantum mechanics. But the multiverse interpretation is the cleanest, simplest interpretation, because you simply drop one of the postulates of quantum theory. So the multiverse theory is actually simpler than the quantum mechanics that I teach at City University of New York. By dropping the postulate that you make an observation and the wave function collapses to actually simplify quantum mechanics.
Would you agree?
No. No, I don't understand all that. I mean, you've got to. The idea is I mean, this is the many worlds. What's that got to do with the other things? There's so many things which seem to be brought in relation to the multiverse that I'm really confused about what's being talked about. I mean, quantum mechanics, yes. If you don't have the collapse going on in quantum mechanics, you have all these superpositions going on which we don't see in the world. Something you've got to do about that. But what's that got to do with the multiverse? Just postulating that they're all there doesn't help. And that's a different multiverse. Anyway, it's not the multiverse where I don't know. I really get very confused about how these problems are resolved by having a multiverse. It doesn't to me help anything.
If experimental evidence for the multiverse is at least short on the ground, if not impossible, what's driving the multiverse story? Is it because Big Bang theory is in trouble and we need something to solve that? Is that what's driving it, Sabine?
Well, so to some extent that's a sociological question about why do physicists do what they do, but maybe it's worth saying a little bit more about the question about the Big Bang theory being in trouble. I can only guess what Michio was referring to when he was talking about the gravitational waves in the early universe. I suppose there was the B modes in the CMB, is that right?
No.
No?
I'm talking about a future generation of space-based gravity wave detectors like LISA, Laser Interferometry Space Antenna, being pushed by the European Space Agency and NASA.
Yeah, but what's the signal? Primordial gravitational waves.
That's right. Gravitational waves before 300,000 years after the Big Bang, at the instant of creation itself.
Yeah, right. So why would this be evidence for the multiverse? I suppose because you say it would be evidence for a particular type of inflation. Is that the idea?
No, because once you have data from a trillionth of a second after the Big Bang, you can run the videotape backwards and see what alternate universes a trillionth of a second before the Big Bang match the data a trillionth of a second after the Big Bang. And so in other words, in this sense, we can actually get data from before creation itself, from before t is equal to 0, by extrapolating post-Big Bang radiation to the pre-Big Bang era. And then, of course, string theory gives you a number of predictions about the pre-Big Bang universe. That's what string theory does. It gives you finite results for everything. And so you can actually calculate the pre-Big Bang radiation and compare it with the post-Big Bang radiation of gravity, space-based gravity wave detectors.
Yeah, but what's it got to do with the multiverse?
Because this allows you to extract out the key universe that set everything in motion, and then you know which of the multiverse ideas is the correct one. Just like Newton's laws. Newton's laws has an infinite number of solutions for baseballs, rocket ships, for marbles, an infinite number of solutions. Which one is the correct one? It depends on your initial conditions. We do not know the initial conditions of the Big Bang itself. Once we have the initial conditions of the Big Bang, then you can start to rule out universes that don't match. And out of the multiverse, you can get the birth of our universe itself. So starting with the multiverse theory, you then get the theory of the universe itself by running the videotape backwards.
Well, but obviously, just to describe our own universe, we don't need all the other infinitely many universes. So,
but this would help to rule out all the other universes that do not correspond to the experiment.
Well, but
maybe let me step back a little bit. So I'm not saying that all those other universes do not exist. I'm trying to say that science can't tell us anything about whether they exist or do not exist. It's just not in the realm of science. I don't have a big problem when people talk about multiverses of whatever type, if that may be the many worlds interpretation or eternal inflation or the string theory landscape and so on. I get a problem if they say it's science, because it isn't. It's a weird kind of Platonism where scientists come to believe in the existence of mathematics.